Okay, so hi everyone. It's a pleasure to teach this class, and I thankful to the organizer for inviting me. So I'll teach 2 hours, and this first hour will be dedicated on random matrices, while the second hour will be mostly focused on the application of random matrices to population dynamics. So I before starting with this lecture today, I'd like to recommend a book that is actually also freely available on archive that you can see on the slide. So everything and much more than what I'll be covering today is contained in that book. So I strongly recommend it. So first of all, what is a random matrix and why do we care? Well, you are probably familiar with matrices. You know that if I give you a matrix, you can typically compute the eigenvalues and the eigenvectors, and there are a lot of theorems that relate uh, eigenvalues and eigenvectors with different properties of the matrix, and everybody's happy. Random matrices are matrices where the coefficient of the matrix are drawn from a given distribution. And the typical problem of random matrix theory is define the properties of eigenvectors and eigenvalues, and more specifically, the statistical properties of eigenvalues and eigenvector, and how these statistical properties are connected to the statistical properties of the matrix or the matrix ensemble we are studying. Okay, so this lecture will be divided in roughly 4 parts. In the first part, I will introduce some motivations, historical motivations, and application of random matrices. The second part will be dedicated on the typical tools that are used for symmetric or emission matrices. And then I'll carry out a calculation using the replica trick to compute the spectrum of random matrix with Gaussian entries. And in the fourth part, I will introduce some tools that can be used to study non-Hermitian matrices using quaternions. Okay, so let's start with the motivation. The first, besides mathematician, the first physicist who was interested in random matrix was Eugene Wigner, who in 1951 was interested in studying the energy level of heavy nuclei. And heavy nuclei are composed of more than 100 protons and neutrons, and so it's very hard to solve exactly this problem. And he was trying to find alternative ways. And so the idea was that instead of studying the actual properties of the nuclei, he was imagining that the Hamiltonian was a random Hamiltonian with random coefficients. And then the question was, what are the properties of the energy levels? And so what are the properties of the eigenvalues of the Hamiltonian operator? And he obtained that the properties of the spacing between the statistical properties between the spacing of the spacings between energy levels were well described by this kind of random Hamiltonian. And here is reported a very nice quote from Freeman Dyson, who was describing the sort of idea behind Eugene Wigner approach. So this is was the first application of a random matrix to physics, or in general beyond like a pure abstract interest in mathematics. But they received a lot of attention in different fields. They has been used to describe the disordered harmonic solids. You can imagine that an harmonic solid is basically a set of balls connected by springs, and when it's random, it means that the spring constants are random variables, and then since the characteristic frequencies are the characteristic frequencies of these disordered harmonic solids are the eigenvalues of the corresponding matrix, and therefore, if solid is disordered, these coefficients are random, and so the problem can be translated into a random matrix problem. Another very famous application is due to Phil Anderson in 1958, who was interested in studying the motion of electrons in a random medium. And instead of a possible way to model this disorder medium, like a crystal with impurities, is to imagine that the Hamiltonian has some random properties. And again, as you can imagine, then solving this problem, studying the energy levels, studying the localization of the eigenstates becomes a problem of random matrix theory. A more recent application that is actually going to be the main focus of the second lecture is in dynamical systems. So Robert May, 1972, was interested in the stability of large ecological communities, and he assumed that there was some dynamics not specified, and these dynamics had a fixed point. And then, if you're interested in the stability of these fixed points, what you can do is that you can linearize the dynamics around this fixed point, and the stability is determined by the eigenvalues of the linearization matrix. And in particular, the system is stable if the largest part of all the eigenvalues of this matrix is negative. So instead of studying a specific model specifying what kind of population dynamics model he wanted to study, he said, let's completely skip this step and let's model directly the linearization matrix, so this matrix A as a random matrix. And in this way, he obtained a criterion for the stability of the system depending on the statistical properties of this matrix. The fifth motivation is the spread of disease. You can imagine that there is a sort of standard model of disease, something like the Ising model of disease, of infections. It's called SIS. And you can imagine that there are individuals that are in two different states, susceptible and infected, and they can transition between these two states. And then the probability that an individual is going to be infected at the next time is the probability that he's not currently infected and is in contact with somebody else. And then there is a rate of recovery. This equation is expressed by a delta. And the key point is that this equation, that is again is a sort of standard equation in disease spreading, disease dynamics. This equation has two phases. If the recovery rate is large enough, then the disease doesn't spread, and basically there is the fraction of individuals infected at any time is close to zero. If instead delta is smaller than a critical value, then there is a finite fraction of individuals that are infected, and the critical value of this parameter is given by the largest eigenvalue of this matrix A, which encodes the probability that two individuals are in contact. So again, studying the properties of these contact matrices and studying actually their eigenvalues gives important information about whether a disease spreads or not. And finally, random matrices have a lot of applications in statistics. So imagine that you have a large data sets where there are, let's say, the expression of n genes in p individuals, or the sport performance of n different sports in p individuals. And in general, these vectors, let's say the expression of the genes across individuals, are correlated. So in data sets, it's very important to, if you have a data set of, let's say, gene expression in people, you want to know whether there are, for instance, community, if there are like healthy people and sick people, and they have different gene expressions, and what genes are mostly affected by that. And when you want to infer the significance of your results, you need a known model, and random matrices where you have random vectors and you build a random correlation matrix are sort of the null expectations that you should compare the results to. Okay, so this is the motivation. we can now move on the tools that are used for Hermitian matrices.